Some of the times we'll need to manipulate these multiple rationals to just get one rational. But most of the time, in this lesson and moving forward, we are going to be evaluating rational expressions that look like this. Polynomial divided by a polynomial. Okay? Now, whenever you saw a polynomial, last unit, oh, this is perfect. The emergency is going off again, so I can catch you guys if you have a phone. Okay. Whenever you saw a polynomial last unit, what did you do? Like if you saw x squared minus 2x minus 3, just look at that. What did you do? Tell your neighbors. Yeah, cool. So like step one, guys, always is to take your polynomials on the top and the bottom and factor. Because it's going to give you a better idea of what's going on. So factor the top and factor the bottom. It will help you. Okay. What was the next thing that we would do after we would factor? No. We didn't have a fraction last unit. Ford? Last unit, after we factored a polynomial, what would we do? Find the zeros. This is important for this unit. All of the zeros, whether they're in the numerator or the denominator, are important. So we will be able to say, hey, x equals 3. That's going to be an important number. X equals -1. That's going to be an important number. We also see that in the denominator, x can equal -1. Okay, we'll keep that in mind. We'll just have it written down once. Maybe we can talk about maybe multiplicities, but who cares? And here, x equals -4. That is an important number. Every single time we want to analyze and eventually graph a rational function, we are going to want to identify the zeros of the top and the bottom. Okay? So we're going to look at this one pretty much for every single page for the rest of our notes. Tell me what are the important x values for this one. What are the important x values? Cool. The important numbers for x plus 5 times x minus 4 over x minus 4 times x plus 3 is x equals -5, because that's a 0 in the top. X equals 4, that's a 0 in the top and the bottom. And x equals -3. Got you? Okay. Now, our goal is to be able to take this and understand what is going on at these three locations, and eventually understand what our graph is going to look like. Now, I went ahead and graphed this. And here's what rational functions look like. Different than polynomials. Not just smooth curves with humps and specific end behavior. You can tell we're not coming from an infinity and ending up at an infinity. Here, we kind of flatten out to the left and flatten out to the right. All of a sudden, we have a missing piece of graph where we don't have anything going on. It looks like we have a nice point, say at -5. 0, that's a nice point. But then when I pop over here, it's a 4. It gives me an undefined. I want to hold it, but I can't. All right. It gives me an undefined. It's what do you mean it gives me an undefined? It looks like there's a point, but they're telling me that no, there's actually not a point there. Okay? So we will have to make some investigations, and we'll have to be able to determine why do we have a 0 at x equals -5? Why do we have what's called a vertical asymptote at x equals -3? Why do we have a missing point with a location at 4, what we'll call a hole? Okay? Cool? So let's investigate. No. First things first. Let's examine. We're going to have example and we're going to have our example. Our example all comes first. Let's look at x plus 5, x minus 4, x minus 4, x plus 3. You know what? I kind of just want to just cross this out and just go. I'm going rogue. Going rogue here. Okay. We identify -5, +4, and -3. Please tell me what you get if you plugged in -5 into your y equals equation that we looked at the graph of. What do you get when you plug that in? Tell your neighbors. I'm going to be pretty simple with this. I get 0 times -9 over -9 times -2. I get 0 over +18, or I get 0 over -2. Maybe that's a better thing. I could cross out those -9, and I just get 0 over -2. 0 divided by anything is what? Tell your neighbors. This is important. This is 0. Okay. So, pop down here. Guess what? While we are examining these rational functions, we find that our zeros, or our x-intercepts, where's my boy? Zeros are my x-intercepts, will occur when I plug in an x, and I get a 0 divided by a number. 0 divided by a number is a 0. That means plug in x, you get y equals 0. That's a location of an x-intercept. Here, x equals -5. Got a 0 over a number. This is my 0 location or my x-intercept. Okay? So, if I said, hey guys, what are the zeros of this function? Whenever you get 0 divided by a number, you get 0. Figure that out. Now, step 1, reminding everybody, including birthday boys, step 1, always look to factor. You see polynomials in the numerator and the denominator, always look to factor. I'm going to factor this to be x plus 4, x minus 4. This is x minus 16. Well, I get interesting points, x equals -4, x equals 4, and x equals 16. Only one of them will produce a 0 divided by a number. Actually, two of them will produce 0 divided by numbers. Not 16. If I plugged in 16, I would end up with a number divided by 0. We will talk about that later, but that is not 0. -4 and 4. I get 0 divided by something if I plug that in. That's a y coordinate of 0. Y coordinates of 0 mean we have zeros. Boom. We've located our two zeros. X equals 16 is not the 0, but it is an interesting location that we're going to have to worry about. So, we see with our graph, x equals -5. Boom. This is 0. Skip domain, we'll come back to it. Actually, start a domain. We can reword this domain of rational functions into what aren't you allowed to have in a fraction? Like, when we have a fraction, what's a bad number in a certain spot where it breaks the fraction and we don't get an answer? Tell your neighbor. Yo, you're not allowed to have zeros in the bottom. Guess what? A number divided by 0. We'll talk about what that means, but that is undefined. We don't get a value. If you ever get a 0 in the denominator, you don't have a point. 0 divided by 0 as well is not defined. If you plug 0 divided by 0 into your calculator, it's going to be like, yo, I can't divide by 0. So when I'm asking you, yo, what's the domain of a rational function? I'm asking you, where are there missing points? And when you have a 0 in the denominator, you have a missing point. You don't have to flip back. I'm just going to show you. X equals 4 and x equals -3, put zeros in the denominator. That means I don't have defined function values at 4 and -3. Let's look. At 4, you saw an und. That is a missing point. I don't have a defined value at 4. Oh, I had it. I nailed it. And that's all. At -3, I don't have a defined point. I have a missing point. There is nothing over x equals -3. So we notice that when your denominator equals 0, you don't have a point. So maybe if we wanted to, we could go back here and we say, you know, there's missing points. Or it's not in the domain. So when I'm asked to find the domain of a function, you're really asking, where are there missing points? What are the x values that you can't plug in? So when you have a 0 in the denominator, you're going to have missing points. Find all of the values that make the denominator 0. What's the first thing we always do? Factor the polynomial. Go. Now, there's one thing I haven't done yet that a lot of you might think of doing. Many of you might look to cross off the factor x minus 2 that's shared. Don't do it. Just leave everything factored, and we are going to do further analysis later. But don't start crossing things off, because if you start crossing things off, stuff is going to disappear on you. Here, we get important values. The top could equal 0 at 2. The bottom could equal 0 at 0. Oh, at 2 as well, and at -1. If I plugged in 2, I get 0 over 0. Oh, 0 in the denominator. This is a missing point. You're not allowed to divide by 0. If you plugged in 0, you get a number over 0. Oh, this is also a missing point. Oh, if I plugged in -1, I'd have a 0 in the denominator. That's also a missing point. So all three of these values are not in the domain. So what is the domain? You could plug in any x into this function, but don't plug in 0, 2, or -1. That's the domain. Okay? You'll be asked, like, what's the domain? Like, where are the values that we have points? It's easier to answer where are the values where we don't have points. You're never allowed to divide by 0, so boom. All right. Let's go back to our friends. Y equals x plus 5, x minus 4, x minus 4, x plus 3. Write that down. Whenever we have polynomials, we like to factor. Well, we have a polynomial on the top and the bottom. Boom, things are factored for us. This is great. If it wasn't factored, we would factor. But let's just stop right here. Great. Okay. Again, we found the zeros of our polynomials in the top and in the bottom. We got x equals -5. We got x equals 4. We got x equals -3. Write those three numbers down. We've already identified one of them as something. Which one did I identify? What is it and why? Remind your neighbors. Which one did we identify and what is it? Tell your neighbors. Don't look back. We've identified that -5 is a 0. Why? Because when we plugged in -5, we got 0 over a number. 0 divided by anything is 0. Cool. Now let's plug in -3. Everybody plug in -3 and tell me what you get when you plug in -3. But let's be a little bit more specific besides undefined. Just tell me what you get. Like, what are the values you get in the numerator and the denominator after, like, multiplying things up? Plug in -3. That's what I'm looking for. Hold on, McCarty. You're working too far advanced. If I plug in -3, I get 2 times -7, which is -14 over -7 times 0. Okay, that's 0. Cool? You with me, McCarty? Okay. Now, the question is, 0 over a number equals 0. I know this is undefined, but I had two situations for undefined in this graph was these. At -3, I have this kind of undefined, a vertical asymptote. At 4, I had this kind of undefined, a missing point that created a hole. So we can see visually that x equals -3 is a vertical asymptote. But the key that we're trying to figure out is why does a number over 0 tell us that that's a vertical asymptote? Why? Tell your neighbors. Why is that a vertical asymptote? Why? No, but why? Why? Saying you gotta tell me why. You can't just tell me, oh, my teacher told me that if it's a number over 0, it's a vertical asymptote. If it's 0 over 0, it's a hole. But why? I mean, we'll figure that out. Yeah, but why does that make it a vertical asymptote? Okay, so here we go. Let's investigate why. Guys, the key to why is one a vertical asymptote and why is one a hole is limits. Okay? Limits. Limits are going to be used often. Now, here's what I'm going to do. I'm going to take this number, -14, I'm going to switch it to a number like 5. And I'm going to think about 5 over x, and I want x to approach 0. It's not going to equal 0, but it's going to approach 0. And we are going to kind of show how 5 over x, what happens to 5 over x, as x gets closer to 0. So let's start with 5 over a half. We're starting with a small value, but we're going to get that value close to 0. Tell your neighbors, what's 5 divided by a half? Tell your neighbors. Good, 10. So this is 10. Let's have x approach 0 some more. What's 5 divided by a tenth? Cool, we get 50. Let's get this x value closer to 0. 5 over 100. 500. What's 5 divided by, let's get this x value closer to 0 by making it an 1,000th. What are we doing? Well, no. What is happening to 5 over x as x approaches 0? What are these values approaching? Tell your neighbor. We are approaching an infinity. As I plug in values closer and closer to -3, what happens is I get a number divided by something closer and closer and closer to 0. If you take a number and divide it by something close to 0, you get something very large. If you take a number and divide it by something close to 0 and it's negative, it'll be very large and negative. This is the whys behind numbers over 0 mean vertical asymptote. So, number over 0, boom. You get a vertical asymptote, and this is the why. Because as this gets closer to 0, the division of this number by this number close to 0 will produce these bigger numbers on both sides. Great. From now on, you can remember that, or hopefully embrace that. But as long as you remember a vertical asymptote, your indication is you get a number over 0. That works too. So now we have identified the location of a 0. We've located the vertical asymptote, and we understand why. So tell me, where does this one have a vertical asymptote? Now, McCarty, you factor x cubed minus x squared minus 2x, and you tell me where you have a vertical asymptote. No. This one.
Oh.
Do this one. I did. Okay. I guess we did factor it up above. We have x minus 2. We have x times x minus 2 times x plus 1. Again, just like what we did. We identify the zeros. I got a 2, I got a 0, I got a -1. We identify which one of these zeros will produce a number over 0, because that's a vertical asymptote. 0 over a number is 0. If I plug in 2, I get 0 over 0. We have not talked about 0 over 0 yet, so this is not a vertical asymptote. It is an important value. Well, we saw it, and we're going to investigate it. Yes, it's the whole. This is the whole. We're going to investigate it, but if we're talking about just vertical asymptotes, if I plugged in 0, I'd get -2 over 0. Okay, boom, check. If I plugged in something close to 0, I'd get -2 over something close to 0 would produce something very, very large and either positive or negative. If I plugged in something close to -1, I'd get something close to -3 and something close to 0. Divide the 2. Don't divide by 0, you're not allowed to. But divide by something close to 0, you're going to get a very large number, and that is why that's a vertical asymptote. Okay. Now, The last value we need to investigate is x equals 4. Okay. Go back. Go back to y equals x plus 5, x minus 4 over x minus 4, x plus 3. We found zeros at negative 5. We found a vertical asymptote at negative 3. We found the 0 because 0 divided by a number is 0. That was our 0 location. We found negative 3 was a vertical asymptote. Why? Because we think about the concept of a number divided by something small, and we get something very, very big. We get an infinity, so that's our indication that this is a vertical asymptote. Cool. Now, let's plug in 4 when my cursor comes back. What'd you do, Caballero? Can you copy down what we have? Do I have to look over your shoulder? Stay with us. Stay with us. Do you guys drink caffeine? You should drink caffeine. You do? All right. There you go. Vertical asymptote. Cool. All right. Now, if I plugged in 4, I'm going to get 0 over 0. Hello, Reti. That's fine. We missed you. What are you doing right now, anyways? Did you win? All right, good job. All right, we're going to get 0 over 0. Now, 0 over 0 still means missing point because you're not allowed to divide by 0. Okay, so we know that we're going to get a missing point. We know that x equals 4 is not in the domain. We don't have a point at x equals 4. But let's think about using a limit again. Okay? Let's think about plugging in something close to 4. Now, before we get 0 over 0, go ahead and write out all of your factors with 4 plugged in. Write them all out with the multiplication and don't simplify. Okay? Plug in 4 everywhere and write out what you get. What I mean by that is 4 plus 5 is 9. 4 minus 4 is 0. 4 minus 4 is 0. 4 plus 3 is 7. Right? Now, is this 0 over 0? Yes, this is 0 over 0, but pause. Pause. Let's think about what would happen if I plugged in something close to 4. Okay, now I'm not going to do this. We're just going to think about it. This would still be something close to 9. Cool? If I plugged in 4.0000001, we're thinking about plugging in 4.000. Thomas, we are plugging in 4.00001, something close to 4. Add 5, something close to 9. Cool. That number minus 4. Do we get 0 exactly? No, we get a number very close to 0. Does it have value? Yes. Is it 0? No, it's close to 0. So pretend this number isn't 0, but rather 0.0000001. Cool. If I took that number and subtract 4, this number is the same as this number. It has value. It's 0.0000001. This number is close to 7. Now, watch what we've done before. If you have 2 times 3 over 3 times 4, you've said you can cancel these 3's and they go away. Well, you can't cancel zeros and let them go away, but you can cancel numbers that are close to 0. You're not allowed to divide by 0. That's bad. When I plug in 4, I get a 0 in the denominator. That's bad. But I can see that if I plug in something close to 4, I'm not going to end up with a number divided by 0. I'm not going to end up with an infinity. I'm going to end up with an actual location, 9/7. If I plug in something close to 4 into this y, I get something close to 9/7. This is our bells and whistles going off saying, hey, you are not approaching larger and larger values. You're approaching a very specific y value. We have a hole. And the hole's location is at 4/9/7. Let me show you on the graph. I could type in 4/9/7, and it's going to be right on top of my graph, right at that correct spot. Four, 9/7. Boom. It's right there. However, it's not a point on the graph. It is a hole. We went over it for undefined, but we can see it has a location. It's not going to be an infinity. What this means to you guys is zeros over zeros are indications that you have holes. Guess what? You're going to need to find the location. Now, here's how we find the location. I'm going to tell you it again. I don't want you to cancel things. I want you to keep things factored, find the x's that make the top and the bottom 0. Yeah, limits are in our lives in this class. Got it? Which one of these three numbers produces 0 over 0? Tell your neighbors. 1 is the location of a hole. It's the location of a hole because you get 0 over 0. But before getting 0 over 0, what did you get? 0 times 4 over -1 times 0. Now, we're not going to say they're exactly 0. We're going to think of these values as being close to 0. If I plug in something close to 1, I get something close to 0. If you have these values that have value and aren't 0, you could say, well, I can cancel those zeros. And I get -4, which is telling me if I approach 1, my function approaches -4, this is a hole, and this is the location, or that's the location. You are responsible for using limit notation to find locations of holes. In the past, you guys just listed off the point. You have to do limit notation. Depends on the question. So, hole at 1. What's x equals 2? Tell your neighbors. Is it a 0? Is it a vertical asymptote? Is it a hole? Tell your neighbors. Why is it a vertical asymptote? Because you get a number over 0, and you know the idea about something divided by something small or something big. X equals -3. What's that? 0. It's a 0. Why? Because 0 divided by anything is 0. This is why, and this is you guys understanding the lesson. This is a vertical asymptote because you get a number over 0. This is a 0 because you get 0 over a number. This is a hole, 0 over 0. You have to find the location. Boom. Find the hole for G. Tell me the location. Okay. Thank you. And use limit notation because I asked you to.
I'm thinking.
No, you're not. Find the hole and its location using limit notation. You guys, it's almost like you guys think that you're not going to see me for like another week. Oh, shoot, that's true. It's almost like you guys are treating this lesson like something you're going to forget because you're not going to see me in like 7 days. Oh, wait, that's true. Okay. Well, anyways, focus up. Finish up. Lock in. No, you're not. You're not locking. You're not factoring right now. Factor. Go. We're doing this one. We just did this one. I literally just did that one. It's right there, Wood. Yo, you need to turn your chair. I don't like people who can't see the board because then you're going to be like, oh, I don't even know what's going on. Right, look, get snuggled up with cold chicken. That's going on YouTube, by the way. If you factor out an x and you got x squared minus 1, you can factor that. Yes, that's not right. You're better than that. No, that's not right. Is it negative 2/7 or positive 2/7? So, coming back over to the Woods table, let's see how we factored x cubed minus x. Okay, just put that x approaches 1 right underneath the LIM, and then it's perfect. No, you guys are sloppy with your limit notation, so some of you lost your only point on the test for not providing limit notation. So, jump on board. You need to know it. You'll need it for calculus. X squared minus 1 is a difference of squares of x plus 1, x minus 1. The bottom, x minus 6, x plus 1. There it is. Okay. The important points are 0, -1, 1, and 6. The 1 point that produces a 0 over 0 is x equals -1. If I plugged in -1 into g of x, I would get -1 times 0 times -2 over -7 times 0. Now, we're not getting 0 because when we talk about limits, we talk about getting close to, not exactly. If I plugged in something close to -1, these zeros are just numbers that are close to 0, and those numbers can cancel. Now, it still means we have a missing point at -1, which is why when I teach this, I don't get rid of these x plus 1. Because I see so many students cross things out too early, and then all of a sudden the hole's gone. And you forgot about the hole, and you get everything wrong. You leave everything in factored form, you identify all your zeros, and when you get 0 over 0, do a little bit more investigation, and you get -2/7 is the location of the hole. What's wrong, Elander? I got a -1, I got a -2, and I got a -7. Plug in -1 minus 6 and -1 plus 1. Okay. Hey, I could give you this. Linda, what do you see in the top? What do you want to do with that? Yeah, you're right. What do you see in the bottom, Linda? Sorry. What do you want to do with that? That's what you do, guys. So guess what? Oh, everybody's in, I don't know limits this semester. Well, just like start factoring the polynomials. Go. You see polynomials, factor. Like, oh, do this. It's a limit. It's like, just factor. Just let's start by factoring, please. But you better have the factor form down, or I'm going to be set up with you. Now, everybody, limit notation. The X arrow 2 is right under the LIM. You guys are writing it out too big. It goes right underneath the LIM. Please embrace the correct way to write the limit. Just like that. Now, that's not the answer. But they're asking you, hey, if you plug in a value very close to 2, what do you get? Well, if I plug in a value very close to 2, this is a number very close to 5. This is a number very close to 0, but it's not 0. This is a number very close to 4. This is a number very close to 0, but it's not 0. These numbers very close to 0, but not 0, can cancel. Turn into 1. 0.001 divided by 0.001 is 1. Okay, so those turn into 1s. Boom. We just found your limit is 5/4, or more importantly, that function has a hole. The hole is located at 2, 5/4. Let's just write it that way, too.
Whoa. You can't do it then. Keyboard. Airport.
All right.
Airport.
Hey. An all-encompassing example. Please do the following for me. Identify the zeros, the holes, the asymptotes, and if you have a hole, tell me its location using limit notation. Go. I want locations of zeros, locations of holes, locations of asymptotes, and if it's a hole, tell me its location. And this is what we finish up on. Go. Everybody do it. I could simplify 6/8. And your limit notation is still a little bit off. It's always the limit as x approaches of the function equals. When you say equals, it's actually meaning approaches. X equals -3, x equals 3, x equals -5 are important zeros in the top and the bottom. X equals -3 gives me 0 over a number, that's a 0. X equals 3 gives me 0 over 0. That's a hole. Do some further investigation. You get 6 times 0 over 8 times 0. These aren't zeros, they're close to zeros because we're plugging in close to 3. I get 6H, which is 3/4, that's the location of my hole. And if I plug in 5, I get a number over 0. I don't care what the number is right now, but I will next class. And I get a vertical asymptote. There's some other fun questions you'll see on your homework.
Oh yeah, we have a whole slide day.
Yeah, you guys got a lot of time to